This domain is Security Architecture and Design Objectives. This domain is founded on the premise that all of our valuable information assets are stored and processed on computers. So this poses the problem. How do we ensure that the computers that we specify and acquire that hold our valuable information assets can remain secure and protect the confidentiality, integrity, and availability of those valuable information assets? First, what we're going to do is walk through the computer architecture, and that includes the hardware itself, the components, the major components of a computer system, and then the operating system that sits on top of this. So this domain deals principally with how to design, specify, manufacture, deliver, install, and maintain a computer system, that's the hardware and the operating system, so that it protects the confidentiality, integrity, and availability of these valuable information assets. We'll look at some operating system protection mechanisms. Then we're going to look at how we might need to implement this security architecture within the organization, within the enterprise. From there, we're going to look at some access control models, and these are academic, abstract models which many security principles are founded on. These are, again, mathematic, they're abstract, and you won't exactly see these implemented in the real world in their formal and complete sense as we're going to be reviewing them. So don't be too concerned about the fact that these are abstract and you won't be able to just check a box in the operating system to enable one of these models. They are taken bits and pieces from each of these models to satisfy the security objective that is required for that particular system or operating system or application. Then we're going to look at how the government, principally the government, specifies to manufacturers what the security needs are for different classes of computers that are required for government use to hold these valuable information assets. And finally, we'll wrap up with looking at the certification and accreditation processes that the government uses when they go to specify and acquire computers to hold their information assets, again, at varying security levels. So first, we're going to take a look at the hardware that goes into the computer system that holds our valuable information asset. We're going to look at the computer itself, the CPU and the components in the CPU, and then we're going to look at memory, the types of memory that we use, and then we're going to look at applications, processes, and threads. There are many layers to the computer system and the operating system and applications that sit on top of this, and then of course the users that actually perform or require the information that is being stored and processed by the computer system. All these components must work together and again ensure that we maintain the security of these valuable information assets. The heart and soul of the computer system is the CPU itself. There are many types of CPUs or central processing units, and the operating system and the CPU must be designed and integrated to work together. We'll look now at the different components inside the CPU. That includes registers, which are small sections of memory, very high speed memory, very close electrically and physically to the CPU itself. Then we'll look at the core of the CPU, that's the arithmetic logic unit. This guy does the vast majority of the work inside the CPU. And then we have the control unit. The control unit acts as a traffic cop and coordinates the motion or the movement of instructions and data into and out of the CPU while it's being processed. First, we'll look at registers. Again, a register is a small storage area. It is memory, very high-speed memory. It's generally located physically on the substrate that is the CPU itself. It is immediately accessible to the CPU, so the CPU can read directly from it and can write directly to it. Next is the ALU, or the arithmetic and logic unit. The ALU again performs most of the work inside the CPU. He's the guy that does all the math and all the logic functions inside the system itself. The control unit again acts as a traffic cop. It's the control unit's job to coordinate the instructions and the data that is going to flow into and then out of the CPU. If the control unit is doing its job well, everything moves very smoothly and efficiently. This is a great diagram that shows how the control unit first aligns instructions and data into generally what's called cache memory first. We'll talk about cache memory in a few moments. Another term for instruction, by the way, is a thread. This instruction that we see in the diagram is actually also referred to as a thread. It is the actual process or small component of a process that the CPU is going to be working on. So the control unit first takes instructions and data from the cache memory area, which again is another storage area we'll be referring to momentarily, and he then directs those two components, the instructions and the data, into the registers. By the way, another word for register is a buffer. A buffer is also a register. So the control unit aligns the instruction and the data into the register, waiting for the CPU to finish whatever work he's doing at the moment and become available. When the CPU does complete the processing that he's performing at that point in time, the control unit then instructs the instruction and the data from the registers to proceed into the processor for the actual processing work. There are two types of registers. We have general registers, which we just saw. The buffers that we saw in the preceding diagram, these would be considered general registers. But then we also have special registers that are used more for control. One of the components that is significant here is the program status word. And the program status word we'll be discussing a little further in just a moment. The significant component about the PSW is that it holds the bit, the flag, that identifies whether the particular component of processing, the thread and data, is operating in what's called user mode or operating in what's called privileged mode. User mode is a lesser trusted mode of operation where we're actually performing work for a subject, and privileged mode is where it is the kernel of the operating system. The most trusted component in the system is the kernel, and in privileged mode we have full run on the system. The kernel is allowed to access any resource or object in the system, whereas user mode is much more controlled, much more restricted. So again, this PSW holds the bit that identifies the level of security that the CPU is currently operating in. This diagram shows at the bottom the hardware, all the components that go together to build this thing called a computer. But the computer itself is incomplete. It's unusable unless we have an operating system that sits on top of it. That's the section in the middle. Starting with the hardware abstraction layer and proceeding upward through the executive services. These are the components of the operating system. Now the section in the blue at the top of this diagram, these are the user's applications. These are the processes and programs that the user desires to run, that actually performs the productive work that the user is trying to accomplish. Next we're going to talk about applications, processes, and threads. A user double-clicks on an icon. It is linked to some executable, some .exe file that has been compiled. That executable can launch one or many processes. Each of those processes can launch one or many threads. In a window or a 32-bit application, this is the way it works. One executable can launch multiple processes. Each process can launch multiple threads. The thread, of course, again, is the small instruction that the CPU can directly act upon. The process consumes resources which are allocated to the process by the CPU itself, through the security system itself. In this diagram we see three processes. Each process has multiple threads, again, thread being the instruction. So again, the thread is an individual instruction, and again, it is a subset of a process. The thread, again, can be directly acted upon by the CPU. Here we see examples of the types of work that individual threads may be performing. Again, thread being a subset of a process being a subset of an application. Processes are in one of three states at all points in time. It's either running, which means it is actually in the CPU and is being executed by the CPU at that point in time. Ready is when the process or the thread is actually waiting for its turn in the CPU, because the CPU can only act on a single thread at any one point in time. At any one instant, a single core CPU can handle a single thread, period. Now the trick here is when the CPU can handle 2 or 3 billion instructions per second, it appears as though it's handling multiple processes and threads simultaneously. In all actuality, it does not. It only handles at any one instant a single thread. So we have running state where the thread is being processed by the CPU. We have the ready state where the thread is waiting for its turn in the CPU. And then finally we have the blocked state where the process is actually waiting for something else, user input, or perhaps it needs data from a preceding process to complete before it can actually have all the information required to move forward and be processed itself. So three states: running, ready, and blocked. Next, we're going to look at how all this works together, how we actually move through individual processes and threads, move them through the CPU. First, we're going to look at interrupts. An interrupt is a polling process that the CPU performs. Processes and even device drivers are assigned different interrupts, and the CPU polls through these various interrupts to see if there's any work that that particular process or driver requires the attention of the CPU for. So again, this is a polling process, and they're called interrupts. There are maskable interrupts and non-maskable interrupts. If an interrupt is maskable, it means it can be disabled or turned off. So we might allocate more time slices to a particular device by masking its interrupt periodically, which means the CPU doesn't poll that device for several time slices. We might also do this for security purposes, to disable less secure processes from functioning while we're trying to complete a more secure process. Processes are maintained in what's called a process table. This is a table that the system maintains to keep track of the processes that are currently being managed by the operating system. Remember, truly, only one process can only have one thread being worked on at any point in time. So we have to keep track of all the processes while they're waiting their turn in the CPU itself. Within the computer system itself, these are used for input and output and to identify areas of memory to either read from or write to. That would be an address bus. And then we have the data bus. Now that I'm latched into this one location in memory, let's flow the information from that memory location in RAM to the cache memory and or buffer memory so that the CPU can work upon it. Here we see an example of the system buses to the right. We have the address buses and the data buses. Again, the wider these are, the more information we can flow with each clock cycle. These address buses and data buses, again, commute instructions to memory and then read data to and from memory so that the CPU can perform the work on that particular piece of information. On the left, we see the processor with the control unit, the ALU and CPU, and then of course we see the clocking. The whole system runs on a clock, so there is a single clock pulse that all components in the system can see, and this way they can remain synchronized with the other components. A 32-bit architecture versus a 64-bit architecture. In the last couple of years, the 64-bit architecture has grown. What are we talking about? We're talking about the width of the address buses and the data buses on the motherboards of the computer systems themselves. The more lanes we have for these data bits, the more information we can commute in a single clock cycle. So if I needed to commute the same amount of data on a 32-bit bus versus a 64-bit bus, it will take twice as many clock cycles to get that data clocked through, because the 64-bit bus has 32 more data bits per clock cycle. Here we see that all components, again, are controlled / managed by the central processing unit. And again, they are all synchronized with that clock signal that we saw earlier. And again, the clock signal that we're talking about is generally the 2.4 gigahertz, the 3.6 gigahertz CPU clock that we see referred to when we go to purchase that computer system. Some definitions we need to get a handle on. Multiprocessing. Multiprocessing implies multiple CPUs in a single computer. So this would be a motherboard that has sockets for 4 CPUs. Remember, a single core CPU can only handle a single thread at any one instant. So if I needed to improve the processing capability of a computer system, one thing I can do is add more CPUs. If I have multiple CPUs in a system, that system could be designed for either symmetric multiprocessing or asymmetric multiprocessing. This is generally defined by the capabilities or limitations of the operating system itself. In a symmetric multiprocessing system, the operating system, the kernel of the operating system, automatically load balances the work that each CPU is performing inside the system. It is mildly adjustable, very slightly adjustable. This is referred to as affinity. However, all in all, the kernel of the operating system manages the load balancing of all work on all CPUs, and it's at his discretion what CPU handles what processes. In asymmetric multiprocessing mode, the operating system supports the assignment of a single CPU for a single or collection of processes. In other words, I can dedicate a CPU to the operating system. I could dedicate a second CPU to my top secret processing of data, and then a third CPU might handle miscellaneous processing, so that I can now isolate the core operating system, some sensitive information, and protect that sensitive information from lesser secure information or processes. Here's an example of a system with actually 2 different systems with multiprocessors. In the left we see symmetric multiprocessing, where we have processor A and processor B, and the operating system automatically load balances those 2 CPUs, and there is little adjustability that we can implement from an administrative perspective. On the right we see asymmetric multiprocessing, where the operating system supports the ability to isolate processes or operating system or programs on 1 or more CPUs. More definitions that we have to look at here. The first definition we want to look at is called multi-threading. Now, this is where an application can manage processing of several instructions or threads at a single time. Remember, the CPU can really only ever work on a single thread at any one instant in time. So again, this is a 32-bit application. 16-bit applications only had 1 thread. A 32-bit application supports multiple threads. So we're implying here when we say multi-threading application that this is a 32-bit app and can support multiple threads, and the operating system can support those multiple threads. The next definition is called multitasking. Multitasking is where we can manage the processing of several programs at one time. And we say at one time. Only one of these programs / processes / threads can ever be worked on at any single point in time on a single CPU system. But because the clock rates are so high on these CPUs, it appears as though we are running 2 or 3 or 10 or 20 programs at the same time. Multiprocessing implies that there's more than one CPU in a system. That supports multiple threads. The more CPUs, the more threads. Recently, the development of the multi-core CPUs has become prevalent. So these rules we're describing here are for a single core CPU, can only process a single thread at a time, With the dual-core CPU, we can now process 2 threads simultaneously. If we do have multiple processors in a single CPU, if we do have multiple processors in a computer system, we can implement either symmetric or asymmetric multiprocessing. The fourth definition we see on this screen is multiprogramming. This implies the interleaved execution of multiple programs on the operating system. This is referred to as cooperative multitasking, which we're going to take a closer look at next. Here we're looking at the difference between cooperative multitasking versus preemptive multitasking. Back in the early Windows days, Windows for Workgroups specifically, they used a time-sharing process called cooperative multitasking. So actually the developer, the programmer who wrote his program says, when I get my turn in the CPU, when he starts paying me attention and working on my threads, I'm going to work this many threads and then I will cooperatively give up my turn. I will relinquish control of the CPU back to the operating system so that somebody else can take a turn. What this says is a couple of things. First, it's up to the courtesy, the generosity of the programmer, how often he gives up his turn. Once he gets his turn, he then can keep it for as long as he cares to. In other words, he could hog the CPU if he chose to. Now, where this caused problems is that because the CPU was waiting for the program to give up its turn cooperatively, if the program locked up or had some other problem where it couldn't reach the statement that says, okay, I give up my turn, the computer system now cannot process any other programs, processes, or threads. In other words, we've just killed the box and it requires a reboot. So back in the Windows 16-bit architecture days, the Windows 3X days, we used cooperative multitasking, and anytime a single app locked up, it locked up the entire CPU and we had to reboot the entire computer. That was unacceptable. So in the days of Windows 9X and Windows NT, the kernel of the operating system now takes control. This is referred to as preemptive multitasking. In other words, program, I don't care what you say when your turn is up. I'm in charge of this computer system and I'll tell you when your turn is up. So in preemptive multitasking, the kernel of the operating system declares when a single process's turn is up in the CPU. And he then controls the time slicing, the sharing of the CPU processor itself. So here are some examples. With cooperative multitasking, Joe's process is only done when Joe decides it's time for him to take a pause. And then he relinquishes his turn to Harry, for example. Harry then gets his time slice and he operates as long as he cares to until he decides to cooperatively give up his turn. He gives that turn up then to Fred, etc., etc. So it's all done cooperatively by the programmer themselves. They decide when they give up their turn. Now with preemptive multitasking, again, the operating system is in charge of when a particular process is done in the CPU, when that process's time slice has been completed. So the kernel remains in control of whose turn it is and when that turn is over. This is an example, this deadlock is an example of when a programmer hasn't written his code correctly. He's implemented or designed in a vulnerability. This is referred to again as the deadlock. This is where one thread or instruction needs a resource, and he can't move forward until he acquires that resource. But a second thread is consuming that resource and has it locked. So the first thread can't move forward because the second thread has that resource locked. The problem is that second thread can't move forward and release that resource until he acquires a resource, which unfortunately the first thread has locked. So what we have here is a deadlock. The program has now crashed. Next, we're going to look at memory. First, we're going to look at memory types. So we have a definition of the different stages of memory that we have in the system. Then we're going to look at how the system protects that memory. That's layering and hiding techniques, which we've discussed in other domains. And then we're going to look at memory addressing. There are some definitions you'll need to know here in memory addressing. So first, let's get a definition of our memory types. We have different areas, different regions of the system that have memory requirements, and some of them are very high performance demands and others are lesser performance demands. The higher performance, of course, is more expensive, so we generally have less amount of these higher performance types of memory. That highest performance type of memory is referred to as the register or the buffer. Now remember, the registers and buffers live typically on the substrate that holds the CPU itself. Then the next level we have is cache memory. Cache memory, there typically are two types. There's level 1 and level 2 cache. Level 1 cache lives on the CPU substrate with the registers and the buffers. Level 2 cache is generally physically and electrically close to the CPU. Then we have RAM. That's random access memory. That's what everybody's aware of. This is volatile memory that loses what it has stored every time you power down the computer system. Next we have read-only memory, ROM. Read-only memory is a programmable memory chip that is not volatile. In other words, it retains its memory even when the power to the device goes away. And finally we have virtual memory. Now because memory of all types are expensive, we very often need to increase the amount of memory that we have in a system, but we don't necessarily have thousands of dollars to throw at this very expensive memory. So what we do is we actually simulate memory on the very slow and very inexpensive hard RAM. And so the memory manager keeps track of the physical address and how it maps to the virtual address that was given to the application. This again is an example of layering and abstraction and data hiding. The application doesn't really know where to find its instruction and its data in true physical RAM. It only calls its locations by the virtual addressing scheme. So this is memory protection by virtual addressing. So the application doesn't really know where his content is in true physical RAM. Further, we see two different memory sticks in this diagram. This could also implement a form of physical segmentation or isolation. We could say that memory stick number 1, the guy at the top, is used only for top secret data, and memory stick number 2, the stick at the bottom, can be used for lesser than top secret information and processing. So we have seen now logical isolation and layering versus physical isolation and layering. Some other memory manager responsibilities include the sharing of information. There are times where one process needs access to information that another process is working on. So we have to have programmatic channels predefined so that there are permissions allowed so that process 2 can access data from process 1. Otherwise, the security kernel would disallow the access and would probably terminate the process that's making the unauthorized attempt. Again, we also had mentioned earlier that the memory manager's job is to provide this logical organization. In other words, setting up the virtual addressing scheme, keeping it mapped, and then also making links or connections to procedures in other areas of memory. And finally, we mentioned the physical segmentation that I described on the preceding slide. So some definitions related to memory addressing. First, we have base address. I believe in the example I described a few moments ago, I declared that application 1 would have an address space that starts at 6 gigabytes, and he could run all the way up to 8 gigabytes. 6 gigabytes would be his base address. Now there's another term here, it's not listed on the slide, called the limit address. The limit address is the offset or relative address from the base address. The limit address is the upper region of memory that an application is allowed to access. So we would say your base address is 2 gigabytes and your limit I'm sorry, your base address is 6 gigabytes. That's where you'll find your processes. And your limit address is 2 gigabytes. So that would tell the application he could run from 6 gigabytes to 8 gigabytes and could go no further. If he tried to touch anything in any other address space, the security kernel for the operating system would probably terminate that process. In other words, the application would be killed. It would no longer be functional. So we have a base address of 6 gigabytes, and if I needed a process that was stored at 100K above that 6 gigabytes, that would be the relative address. So it would be application 1 with a relative address of 100K. The relative address says, starting at your base address, move up. And that's where you'll find the instruction you're looking for. And finally, we have the absolute address. Now, the program or application itself doesn't ever know what its absolute address is. Remember, this is this logical segmentation that the memory manager implements between the program itself and true physical RAM. The program implements or executes its processes, loads them into RAM, but doesn't actually know truly, physically, where they're located on those memory chips. It just knows to tell the memory manager, I need an instruction from my base address plus 100K, go get me that. And then the memory manager looks at his map, identifies the absolute address or physical address where the information is that the program is asking for, and then provides access to that instruction or data set. So here we see an example of the base address and a limit address. The base address would be the 30004, and limit address is how much higher am I allowed to go from that base address. So this identifies the lower and upper bounds of the memory space that an application or program is allowed to utilize. We also need to recognize that from time to time, processes need to share access to data and instructions. We also mentioned this DLL, or the dynamically linked library. These libraries have shared routines. So periodically, these programs or processes need to access the same instructions from these DLLs. So we must have predefined programmatic procedures so that a process is allowed to access a process in another area of memory that is not his. So again, these have to be predefined, complete with permissions, privilege. Otherwise, the security kernel for the operating system will terminate the offending process. And that's exactly what I was describing. Memory protection. Again, when we allocate a program the region from 6 gigabytes to 8 gigabytes in RAM, if some other application or process attempts to, in an unauthorized fashion, access anything in that region, the security kernel for the operating system will terminate the offending application. In the Microsoft operating system, the error message reads, an application has attempted to execute an illegal instruction and has been terminated. You've probably seen that error message. That is an application or process who tried to touch something in a region of RAM that he didn't have permission to. Next, we'll talk about a memory leak. Now, a memory leak is typically the result of poor programming. This is generally where a process has requested a region of memory. In other words, a stack. He said, I need a stack and it needs to be this large so that I can get all my instructions and all of my data into the stack. And then when the process has completed, when the CPU has actually performed the work, unfortunately the programmer doesn't give that stack memory back to the system. And he actually continues to collect more and more and more stacks that he never gives back. As a result, that application consumes an ever-increasing amount of RAM until the system becomes starved for memory. As a result, the performance of the system gets worse and worse, and it could actually cause the system to fail. When a bad guy finds this vulnerability, this poorly written code that's called a memory leak, the bad guy can now tickle that application into making that same request that doesn't give back the memory. He just triggers the process over and over and over again until he effectively kills the performance of the system. This is a denial of service or DOS attack. In this section, we're going to be looking at the different ways that the hardware and the operating system can isolate or segment processes, data, applications, and programs from other components inside the system. This is for security purposes. Let's keep this in mind. The whole perspective here is how to secure our processes and our data that is being worked on by the computer itself. So again, this is a combination of hardware and operating system. So first we're going to look at different levels of trust. And the more trusted a component is, the more resources that component has access to. We'll look at memory segmentation. Now, we've already talked about physical segmentation, where I can isolate certain processes and data set to single CPU chips, and all other processes and data live on other CPU chips. That's physical segmentation. And then we also discussed the memory manager's assignment of virtual addressing to the user level application, so that the application doesn't really know where it lives in true physical memory. That is, again, logical segmentation. These are all different versions of process and data isolation. It's all the same as layering, hiding, abstraction. We are securing instructions and data sets from other instructions and data sets that might be of lesser security or might even be malicious in nature, trying to modify, corrupt, or steal that information. Then we'll look at virtual machines. Now, a virtual machine is a non-physical computer that lives inside the operating system, already running on a computer. Now, we have a host machine, and that host machine can support multiple virtual machines. We'll be describing several different types of virtual machines. These virtual machines are pretend computers, if you will, that live inside this one computer. Each of those machines has its own security systems and mechanisms and can perform processing in this isolated virtual machine. If there's any security breach inside that virtual machine, we simply kill that virtual machine and we have not affected the host computer at all. This also isolates that virtual machine from all other virtual machines. So again, a virtual machine is another way of segmentation, isolation, layering, and hiding. Another way to abstract processes and data from other processes and data. Then we're going to look at something called the protection rings. Now, these are conceptual security boundaries. Ring 0, the executive services of the operating system live at ring 1. Operating system utilities and device drivers live at ring 2. And then all user processes live at ring 3. Ring 0 is the most trusted with the greater security domain. Ring 3 is the least trusted with the smaller security domain. And again, as we've described, closer to the core, more trust, greater access. Further away from the core, out at ring 3, less trust and smaller access, lesser access to resources. So this diagram shows those different security domains. Also, it identifies the need for information to flow from outer rings to inner rings. Now, this information flow, requests and information back out of this ring structure, is controlled through specific communications channels. These are restricted interfaces, and they are referred to as application programming interfaces. Again, this is a functional tool, but it is also where we need to implement security. So they are security components as well. We only provide APIs to processes at higher layers that we choose and authorize access to. So here again we see the hardware at the lower layer, the kernel or the executive services in the mid layer, that's the operating system, and then we see the user level operating at the highest level. And again, we recognize that the user level programs need access to these internal resources that are controlled carefully by the operating system. So these requests must flow down through the specific executive services to request and then hopefully be granted access to the specific resources that the user program is desiring. So again, the application programming interface is the controlled communications channel from one layer to another layer. Again, this is designed for functionality, but from a security perspective, it also must be highly secured. This is the way a bad guy will violate your security. So it's programmed communications channel between two layers, and in the ring architecture or the OSI model or any other layers that we're talking about, abstraction, layering, data hiding, black boxing, all of these, the portal, the communications mechanisms from that layer to any other layer is done through an application programming interface. Again, a key point for functionality, but more importantly, a key point for security. So this should be a carefully controlled interface. We see these interfaces between layers on network components, in protocol stacks, drivers, etc. You see the list here. Again, anytime we're talking about abstraction, layering, data hiding, black boxing, all of these require APIs so that the processes outside a particular layer can communicate with that layer so that it can get its work done and can then provide the output to the next layer as required. So we're going to take a closer look at the protection of different processes. And again, this is to ensure that one process cannot access resources in another process's memory area. So they cannot modify the confidentiality, integrity, or availability of that other process's information. We've already described one area of process isolation, and that was with the stack. As you recall, the stack is a region of memory that is assigned to or allocated to a process on request of the program. It is protected by the security kernel of the operating system, and if an unauthorized process attempts to access any of the information within the stack, the system declares an error and will terminate the offending process. On occasion, this will also require termination of the violated process. Another mechanism used to provide this isolation or protection has to do with encapsulation. And again, this is the layering, the data hiding, the abstraction boundaries, etc. And this affords a level of what we call black boxing. A process at layer 1 has no idea what's happening inside of layer 2. All he knows is that through a particular API, based on a certain set of rules on how the communications will flow, the layer 1 process will hand information through the API to layer 2. And what happens inside of layer 2? Layer 1 has no idea. So this is a way of encapsulation of these processes. Another isolation mechanism is time multiplexing of shared resources. This is where different time slices are allocated to different processes. On a larger scale, substantially more coarse scale, we might declare that a particular computer system is available for processing of top secret data from 8 o'clock until noon. And from 1 o'clock in the afternoon until 5 p.m., we'll use that computer system for processing. So now that we've seen how the computer hardware and the operating system can work together to provide what we call the trusted computing base, we're going to start to look at some details on how we can evaluate and eventually certify a specific level of security that we can be assured our computer system will afford us. We're going to look at what's called the TCB, or Trusted Computing Base. We're also going to then consider something we've already talked about a few times. This is the execution or security domain. Remember, this is the collection of all objects that a subject has access to. We've also referred to this as the user profile, the user's level of privilege as well. We're also going to look at a couple of components in the operating system. We've already mentioned the security kernel, and I believe I even mentioned the security reference monitor. We'll be delineating that a little bit further. And then we're going to look at some details related to the security kernel that are required so that this level of security can be evaluated, tested, and then certified. So the Trusted Computing Base. This is a term coined from the Orange Book. Now, the Orange Book is a collection, it's one of in a collection of books called the Rainbow Series that was developed by the National Center for Secure Computing, the NCSC. And the Orange Book defines if we have a computer system that we recognize is going to hold our valuable information assets, how can we be assured that this is going to maintain the confidentiality, integrity, and availability of the valuable information assets that reside on that computer system? So the Orange Book dealt with security on a single box. We're also going to discuss briefly the Red Book. The Red Book talks about the network behind the individual computers. That's referred to as the TNI, Trusted Networking Interpretation. So the NCSC specifies a list or several rankings of security levels that might be required in our processing and storage of our valuable information assets. As we test and certify a computer system against this standard in the Orange Book, we can establish what we call the trusted computing base at a certain level of security. Again, this identifies then a rigid boundary, or fairly well-defined boundary between what lives within the TCB and what lives outside the TCB. This boundary is called the perimeter, the TCB perimeter. And this perimeter can be penetrated only through very closely controlled and managed application programming interfaces. Remember, the communications channels that are used between layers. Well, here we have two layers. We have within the TCB and outside the TCB. And of course, we then need an API so that our information can flow through that boundary and flow through a very controlled and secure manner. So here's a diagram showing components that live within the TCB. Remember, as we said before, we're talking specifically about the hardware, and that would include the firmware or BIOS that lives inside the computer system itself, and then of course the operating system that is installed on that piece of hardware. This is what lives within the TCB. And the components that are not included in this trusted computing base must penetrate this perimeter, the TCB perimeter, through very carefully controlled APIs. One of the requirements of the TCB from the operating system standpoint is a kernel that protects itself, and it also has trusted recovery, trusted shell, and as it communicates with components outside the TCB, a trusted path for communication. Because if a bad guy can get between the subject and the kernel and inject his malware or violate the confidentiality or integrity or availability of the information, then the TCB is of no value. It's been exploited. So again, we need trusted path, a hardened perimeter, and system self-protection. We've pretty well defined this. This is referred to as the execution domain or a security domain. And again, what this identifies is the collection of all objects that a subject has access to. And related to processes, let's put this in perspective. Processes are only launched or can only be executed in the context of a subject's level of privilege. In other words, whoever launches the process, that process carries with it that subject's access token or level of privilege. And therefore, any of its processes run under the privilege level of whatever subject launched that process. Now, if a user launches the process, then the user's level of privilege is much smaller. The execution or security domain is much smaller. In other words, fewer resources can be accessed directly. If the kernel of the operating system launches the process, then of course the execution domain for this particular process is much larger because the kernel is the most trusted entity on the computer system and has access to many, many more resources. And let's also remember that it is the program status word, the PSW, that is the flag that identifies which execution mode the process is going to be operating within, whether it's user mode or privileged mode. So again, the execution domain or protection domain or security domain, all three of these are the same thing. This is the collection of all objects that a subject has access to. We've defined this over and over again. So what are the objectives or the functions of the TCB? First, within the TCB, we have to, in a secure fashion, be able to launch or activate processes. This is done through that polling process we called with the interrupt requests. Then we have to identify, using the PSW, which mode of operation we're running in. Are we running in user mode, or are we running in kernel mode or privileged mode? So we have to identify which mode we're in and then properly and completely switch into that mode. Then we'll look at some memory protection mechanisms, and again, let's don't forget the trusted path requirements. As I am taking data in and outputting data, those paths of communications, those APIs, must remain secure. So, starting with process activation. Again, this is when we are trying to get a process functioning in the CPU. We want this routine to run. We want this program to run. I need my data output from this program. This is when I need it to be activated. So what happens is this process gets assigned an interrupt, and the CPU, through its polling techniques, will call that interrupt and say, do you have something for me? And because our program is ready and is waiting for the CPU to make this request, boom, our process now begins to interact with the CPU and actually gets its turn in the processing channel. When the CPU has completed all the processing for this specific process, then the CPU sets a flag again and identifies that this particular process has been completed, and will reallocate the resources that had been assigned to this process to the available pool of resources. As we recall, it was the PSW, or the program status word, that is the flag that identifies which execution domain we're going to operate in, whether it's user mode or privileged mode. And we must securely and completely switch between those two modes. Otherwise, it would be possible that a user mode process may get access to information in privileged mode, or vice versa. Both of these would be a violation of the TCB and would be a breach of security. So again, the security perimeter, this is the TCB perimeter, identifies very specifically a boundary that says these components within the perimeter have been tested and certified as maintaining a certain level of security, and anything that is not within this perimeter can only communicate with components inside the perimeter through very carefully controlled APIs or interfaces. So as we said, this perimeter can only be penetrated through very carefully controlled application programming interfaces. This API that we're talking about when it comes to a subject accessing an object is controlled by the security kernel of the operating system, and he takes advantage of another component that lives at ring 2 of the in the ring architecture called the security reference monitor. And the whole point of this evaluation through this API as we penetrate the TCB perimeter is to ensure that the subject who is attempting to make access of an object is doing it in an authorized fashion. And if the subject is an unauthorized subject making this request, then the request will be denied. So again, it starts with a ring 1 executive component called the security kernel. Again, this guy is one of the main components in an operating system, and it's his job to enforce all security-related rules. He's the guy who protects the memory space for one application from another. He's also the guy that implements the security reference monitor that we're about to delineate further here. So the security kernel, a ring 1 component, contacts the security reference monitor, a ring 2 component, and says, we have a subject that's attempting to access an object. Is he allowed to? And the security reference monitor then looks at the process, that's the request itself, and looks at the access token that is associated with that process, who launched this process, and so we now get an identification of the subject that is making the request. then we compare that access token to the access control list, the ACL, that lives with the object that the subject is trying to access. As these two components align, that is the subject's identity or access token, along with the ACL, the access control list of the object, we can now identify what level of access or privilege the subject has on that particular object. Again, this is very carefully controlled and monitored by both the security kernel and his worker, the security reference monitor. So this security reference monitor has three major requirements that must be in place for any operating system to satisfy any level of the TCB. The first rule of this security reference monitor is that it must provide isolation between subject and object, and it must be tamper-proof. That's rule number one. It's a boundary between subject and object, and it cannot be tampered with. Rule number two is every time a subject attempts to access an object, the security kernel, security reference monitor, must be invoked and cannot be circumvented. So it's a boundary and it can't be tampered with, and it gets invoked 100% of the time, cannot be circumvented. Rule number three says it also must be small enough to be tested and verified completely and comprehensively. In other words, we have to be able to attest it and certify that it does provide this level of functionality, and it does it 100% of the time. So three rules. Again, it's a boundary and it can't be tampered with, rule one. Rule number two is 100% of the accesses run through the security reference monitor and it cannot be circumvented. And then rule three says it has to be test-worthy. It has to be testable. And the only way that an operating system could ever comply with the requirements of the trusted computing base are if the security reference monitor satisfies these three rules. So let's pull this all together. Let's look at how a system provides a level of security that can be certified. So let's pull this together now and identify how a system can be certified as being trustworthy at some level of security. First, a security policy or a declaration of what level of security a system is supposed to operate at is defined, and then the system must also enforce that level of security. So it's defined in its security policy, and it is self-enforcing by the system. Second, it also identifies how these rules relating to security will be managed and how the system will protect itself, and also how it will provide the secure access to these valuable information resources. The security reference monitor is the boundary or the API that must be passed through anytime a subject attempts to access an object, and only authorized accesses will be allowed. The security reference monitor is a component of the security kernel, and he is a requirement of the operating system that, of course, is going to be evaluated against a standard in the trusted computing base. And finally, the security kernel provides access to these processes in a secure fashion. In other words, they have boundaries between them. They are isolated from one another so that these processes cannot, in an unauthorized fashion, access another process's resources. So we have boundaries between the processes. That's all within the TCB. And then we have the security reference monitor that controls how external subjects and processes access things within the TCB. And of course, the underlying operating system is self-managing. Now we're going to take a quick look at 4 different modes of access control methodology called Mandatory Access Control, or MAC. We've already identified the requirements, different levels of security for even one single system. There are times where a single system will need to handle top secret data and classified data all on the same system. So we need to be able to specify what those different security levels are, and then have mechanisms in place to ensure that we are able to maintain those levels of security. Mandatory access control is a very rigid and expensive access control methodology. It typically is used only by military and government networks because of its rigidity and its very high expense, but it is also probably the strongest access control model that we have. So now there are 4 modes of operation in a Mac model. First, we have the dedicated security mode. This is where all the information and all the processes on a system are at the same level of security, and all the subjects that will need to access those information objects are also at the same level of security. So in a dedicated security mode, the system will only handle, for example, top secret data. As a result, because all users are top secret users, they have access to 100% of the data. That's a dedicated security mode in the mandatory access control model. Next, we have the system high security mode. And as you read through those bullets, you'll notice that only the last 2 change. So with system high security mode, we recognize that we have different levels of security requirements for the information. That means we'll have different levels of subjects accessing those different levels of objects. And now we need to qualify what users are allowed to access which objects. So with the system high security mode, all users can access some data, but it's based on their need to know. So it's more than just they're at the same level, such as top secret. Now we have top secret and they have to be working on the Afghanistan project, for example. So they need the same level of clearance, but they also have a need to know. And we might have other pieces of data that are top secret, but not related to Afghanistan. Therefore, the first subject that I described would not be able to access that second piece of data. So, dedicated security mode, all users have the same level of access on all the information. On system high security mode, users are all at the same level of clearance, but they have different levels of need to know. And as a result, they might be prohibited from accessing some of the information. On compartmented security mode of mandatory access control, all users have the same clearance, and they may have the same need to know, but they also need formal access approval. So you see we're adding another variable here, and this becomes more and more complex if you haven't noticed. So the security system on a compartmented security mode system is substantially more complex than either of the first 2 we described. And finally, the multi-level security mode adds one more variable. All users have the same clearance level. They all have a specific need to know. They all have the same formal access approval, and now we have different levels of clearance, all on the same system. So we have clearance, need to know, and formal access approval now pulled into this. And again, these are all variables that tie together to make this a more complex, more sophisticated, more difficult security model to implement. So to summarize, we have the dedicated security mode where all users are all at the same clearance level, and they can access 100% of the information on that system. System high security mode, all users have the same clearance level, but their need to know is different. Compartmented, all users have the same clearance level and have differing levels of need to know and have differing formal access approvals. And finally, in multi-level security mode, we have differing levels of clearance, differing categories for the need to know, and differing access approvals. Next, we're going to look at implementing security within an enterprise. And it isn't the perspective of add a firewall here, or let's use stronger deadlocks, deadbolts on the doors. It's more of a complete integration of security within the enterprise. It's designed in from the start. So again, the enterprise security architecture is integrated and it permeates the entire organization. It deals with the personnel, the information systems, the processes, and these are all carefully intertwined with security in mind. This, of course, must also satisfy the business needs of the enterprise, of the organization. Remember, the CISSP certification is a business-oriented certification. As a result, we always must keep in mind what the nature of the business is and maintain that proper business is being performed. Truly, this is all about ensuring and maximizing the profits of the organization while maintaining security. And again, the enterprise security architecture is designed to help optimize the security of the organization, of the enterprise, so that we can endure a long, productive, and financially beneficial business. So what does the enterprise security architecture desire? What are the hopes of it? What are the objectives of this architectural design? First, it's an overall big picture view of security for the organization. It informs the business makers and teaches them how to make proper business decisions, integrating the business needs with the needs for security for that organization. By doing this, we minimize risks. It also minimizes costs related to losses associated with exploits or violations of our security perimeter. Again, it is a business-oriented objective, requirement, and while we do implement technology, we don't simply say we should have a firewall. We should recognize that our business needs dictate security for our network on the perimeter, and as a result, the firewall is the answer. It isn't the initial point, but it is the solution to the business-oriented problem. And finally, it allows us to satisfy many other business-related objectives, such as regulatory compliance and the need for auditing and record keeping for these regulatory and legal related requirements. So if we don't integrate security through the construction of this business, we have numerous problems that will result. First, it leads to ongoing confusion. We might put out a fire here. So in order to implement enterprise security architecture, we need to do it at 4 different levels. First, we have the strategic alignment. This is where we take the high-level view of the business, the enterprise itself, and we evaluate where we need security and what level of security. So that's the strategic alignment as I begin to have everyone in the organization recognize the need for security. And then we look at process enhancement. This is where we actually infuse specific processes with security components to help us ensure that those processes will remain secure. Further, we look at the business enablement. Now, this kind of lives between strategic alignment and process enhancement. So it might have been better as a second bullet, but business enablement is where we actually start to look at specific modules within the organization, within the enterprise, and identify where that facet of my business needs security, at what level of security, and how we might implement security to satisfy those needs. And finally, once we get security permeating the organization, we must always be monitoring and auditing and evaluating how effective is our security, because it's a continuously refined system. We're always evaluating where we've missed something or where we've had an exploit and firming up our security in those arenas so that these exploits don't happen over and over again. So again, strategic alignment is the big picture view where we analyze what is required throughout the organization as far as security is concerned. Now, this starts at senior management. They are ultimately responsible for the security posture of the organization. They will typically hire someone like you and me to advise them on how to implement security within the organization. So they will assign to us the formal responsibility and authority, as well as accountability for the overall implementation of security for the organization. Again, it must be driven by senior management. Oh, one other thing, they also afford us the budget to implement that security program. Then we look at the current security profile. Where are we vulnerable? What are the threats that will negatively affect the... And as we can see here, that we must integrate all of these components together. First, it starts with the security foundation. The security foundation is based on ISO standard 17799. Again, this is the rewrite of the British standard 7799 chapter 1. This is also what we've come to know as the Common Book of Knowledge. This is what the CISSP is based upon. General security principles. How do we implement security in our organization? Then, now that we have this book, if you will, of security standards, we need to align the organization strategically to comply with that book and work with it so that we infuse security throughout the entire organization. And that includes both business enablement and process enhancement with security components infused into both of these aspects of my organization. And then, of course, we need to monitor and evaluate. How are we doing? This is where we implement security effectiveness with our own auditing department and our continuous monitoring and reevaluation. Are we secure? Are we doing this thing right? So how do we pull all this together? Very carefully. It has to be done correctly at every stage. Any one stage done incorrectly, and we might as well just not have ever started. So it requires a complete linear and cohesive security program with internalize and externalize, evaluating, monitoring, and refining the security processes within the organization. This is one of the models that help us map through the implementation of enterprise security architecture. It looks at the who, what, where, when, why, and how we will implement security on information assets in a contextual manner, conceptual manner, logical, physical manner, at the component level and at the operational level as well. So this is, again, a security model to help us implement and evaluate our enterprise security architecture. This model is based more on an industrial model. This is not the CISSP model as we saw in the preceding slide. This is a non-CISSP model, but if you consider this, they have the same problems. And as a result, they have many, many of the same solutions. And while they may slice and dice the boundaries a little differently, the overall objectives are largely the same. So regarding our 3-year security development program, we first start with the buy-in. We have to recognize that we need to implement a security program in our organization. Senior management hires us and assigns us the responsibility, the authority, and of course the budget to design and implement a security program. So we design the principles, the strategy, and the policy, the written policy, and that defines then the security architecture for the organization. Next, we'll deploy or implement the organizational structure for security, and that includes the technical framework that goes along with that security in the organizational structure. Once we have this in place, now we can identify what a security standard is, a baseline. Remember, a baseline is a threshold, and if the baseline is exceeded, then we have an incident, and this requires an investigation. We also then can lend ourselves towards a higher level of auditing, compliance, and certification to give us a level of assurance that our security is effective and complete. We also need to recognize different areas or aspects, facets of our organization have differing security demands. In the example here we see we have the public internet at the top with a DMZ, demilitarized zone, in the middle. This is where our publicly facing web resources are provided to the internet. And then we have another section behind the second firewall, which we would consider the most trusted region of our enterprise. And as we can see, we have many different facets of our network, and we have many different technological tools and components and processes to help me implement and ensure security for all those valuable information assets that are flowing across these wires.